Thank you, Jessica, for the kind introduction. And I'm happy to be here to share with you some of our recent research on human AI decision making. So as we all know, AI technology has made some remarkable progress in the recent years, right? So today, AI has been widely applied in many different domains, from finance to healthcare to criminal justice. And the rapid development of AI technology has also fundamentally changed how decisions are made today. So in the past, given a decision-making task, usually it's humans who will process this task and deliberate about what are the possible options to take and eventually make the decision. But nowadays, AI models have been trained to uncover hidden insights from the big data. And, now given the decision-making task, this decision aids powered by these AI models can actually provide some decision suggestion or decision recommendation, which will later be presented to the human decision makers to assist them in their decision-making. So from the model designer's point of view, of course, the goal is to try to design the AI-based decision aids in a way such that the joint human AI decision-making performance can be optimized. But the question is how. So in order to answer this question, I would argue that we need fundamental advances in some scientific understanding of this human AI decision-making process, which at least include the three key components. The first one is that we really need to have a better understanding of how human decision makers are actually collaborating with AI assistants, right? So if they are presented with AI recommendations, how are they going to interact with the AI recommendations, and how are they going to decide whether to use its recommendation or not? Now, moving on from empirical understanding, I will argue that it's also necessary for us to obtain more quantitative understanding of the mechanism that determines humans' interaction with AI. So this usually involves the development of some computational models so that we can predict what humans will do when they interact with AI. And finally, with this empirical and computational understanding, the last step is for us to think of whether there is a chance to create some kind of interventions to influence the decision makers, and so that in the end of the day, the human AI team can achieve a level of performance that's beyond either party alone. So in today's talk, I'm going to go through 3 projects covering each one of these aspects, and hopefully that will give you a flavor of the kind of human AI decision-making work that my group is working on right now. Okay, so let's start with the first component, obtaining some more empirical understanding of how humans interact with AI. So one of the key part in this empirical understanding is we really want to understand how do humans trust the AI models, and how do they decide on whether to rely on the AI's decision recommendation or not. For example, a question that we may ask is, what are the factors that will influence people's trust or reliance on AI? And perhaps one of the most straightforward thing that people can think of is that AI models' performance will impact people's trust and reliance on AI. So a common metric that we often use to quantify AI's performance is accuracy. So to this end, we have conducted some previous experiments to understand, how the AI model's accuracy, including its stated accuracy on the held out data and its accuracy that people actually observed in the real world usage of the AI model, would affect people's trust and reliance on AI. And we also looked into if there are multiple performance indicators of the AI model, right? Say you have some information about the AI model's accuracy, but you also have some information about this AI's confidence on a particular task instance. How would the presence of multiple performance indicators of AI affect people's trust and reliance on AI? But, in real life, there are also the cases that people have to decide whether they want to trust or rely on AI, even if there is no performance information being communicated to people at all, right? So in those cases, how would people react to AI? So this is the question that we are going after in our first project. So At the first glance, it sounds like without any performance information of the AI, people don't really have a way to gauge about the reliability or trustworthiness of the AI model. But if we think about this statement more carefully, we'll probably say that this statement is not entirely true. We can probably only say without performance information, there is no external or objective way for people to think about the trustworthiness of the AI, but potentially some internal or subjective assessment could happen. In fact, if we look back into the advice-taking literature in psychology, one of the observations that psychologists find is that when human in real life, a lot of times they need to decide whether to trust the advice given by an advisor without knowing whether that advice is good or not. And the way that they make the decision of whether to trust this advisor or not is that they often think about, whether this advisor tend to agree with themselves on some, other decision-making tasks or on some other tasks that they make independent judgment. If they agree, then they tend to think this advisor is, credible, and they're more likely to follow their suggestion. Otherwise, they think this advisor is likely less credible and less likely to follow their advice. And this is particularly true if people are confident about their independent judgment, because when they are confident, they tend to think they're right. So naturally, one question that we will ask in this, in answering our earlier question is whether this can be generalized to humans' interaction with AI, right? So will the level of agreement between human and AI on those decision-making tasks that the human have high confidence about affect people's trust and reliance on AI if they don't get explicit performance information about the AI model? So we conduct a human subject study to try to answer this question. So in this study, what we did is that we asked people to make prediction about the outcome of speed dating event, right? So our participants will be presented with a profile like this, which basically summarize, a pair of participants in a speed dating event with their demographic information, what they are looking for in their romantic partner, as well as their rating for this participant that they meet in the speed dating event. And what we ask our participants to do is to first make their own binary prediction in terms of whether this participant in the speed dating event would like to see their date again in the future. And after they make this initial prediction, our AI model will present to them a decision suggestion. With that, our subjects have the opportunity to revise their prediction and submit their final prediction. So this is a task that we used. And in order to enable our experimental design, we first need to get a sense of on different kind of speed dating outcome prediction tasks, what are the majority prediction that people tend to make and how confident they are. So in order to get this information, we first ran a pilot study. So in which case our decision subjects independently worked on a large set of this speed dating outcome prediction tasks. On each task, they predict they both give a binary prediction in terms of whether the participant would want to see the date again, and they also indicate their confidence in their prediction. So based on this information, we were able to categorize different decision-making tasks into several groups. For example, we find a subset of tasks such that the majority of our decision maker is going to make a correct prediction on those tasks with high confidence. So majority here means more than 80% of the subjects in our pilot study actually make the correct prediction. Now, we also have a group of tasks where the majority is going to be incorrect, but they are incorrect with high confidence. And similarly, we have other two group of tasks where the majority is correct or incorrect, but whenever they make the prediction, they're relatively not so confident in their prediction. So with this categorization of decision-making tasks, now let me tell you more about our real experiment design. We asked our subjects to work on a sequence of 40 these kind of decision-making tasks, predicting speed dating outcome. And these 40 tasks are the same, but they are divided, they're the same for different subjects, and they're divided into two phases, with each phase containing 20 tasks. But we carefully selected what are the 20 tasks that go into each of the phase. In particular, for the first phase, 20 tasks, we selected those task instances that, based on our pilot study, we find people tend to have high confidence in them. Okay, whenever they make prediction, they're making prediction with high confidence. And then we created experimental treatment by varying the decision recommendation given by the AI model. So they can be agreeing with the subject's majority prediction on all the 20 tasks. So that will give us a high agreement treatment. And they can also agree with the majority prediction given by our subjects only on 40% of the tasks. That gives us the low agreement treatment. And we also have a median level agreement treatment. So essentially, in this first 20 tasks in phase 1, the subjects in different treatment will see exactly the same decision-making task, although the order is randomized, but they see different prediction or suggestion from AI model, and the AI model will tend to agree with their own independent judgment to a different degree. And in order to also control for some potential covariant or confounding variables, we also made sure that the AI model we presented to people in phase 1, they actually have exactly the same accuracy across treatment. Okay, so that's phase 1. Now, moving on to phase 2, the phase 2 tasks are selected from those tasks that we identified in our pilot study that people tend to have low confidence in them. Okay, so when people make predictions on those tasks in phase 2, they themselves relatively have a low confidence in their prediction. And so we made sure that on this phase 2 20 tasks, subjects across treatment see the same task, but they also see the same prediction from the AI model. So in order to quantify people's level of trust, reliance on the AI model, as well as the perception of the AI model, we both added some survey in the middle of phase 1 and phase 2 in terms of people's perception of the accuracy of the AI model, the understandability, reliability of the AI model, and so on and so forth. At the end of the experiment, we asked them to self-report their level of trust in the AI model. And we also quantify how likely people are going to rely on the AI model's suggestion by looking into phase 2, in which all the subjects see exactly the same AI prediction, how frequently their final prediction is going to be the same as the AI's prediction, and how frequently their final prediction is going to be the same as AI's prediction, conditioned on their initial prediction is different from AI's prediction. So essentially, they switched from their own prediction to AI's prediction. Okay, so with this design, now let me show you about what we find. So essentially, as you can see from this figure, we find that with a higher level of human AI agreement on those tasks that people are confident about, essentially those tasks in phase 1, people report that they think the AI has higher accuracy, they think the AI is more reliable, they think the AI is more understandable, and eventually in phase 2, they also rely on the AI model more, even though, recall, across treatment, the AI model have exactly the same prediction across treatment. Right. So essentially, if you think about this, this is really close to some of the cognitive bias that we see in human beings, right? So essentially, this is like a confirmation bias, right? Like whoever agree with me, I think it's great. Whoever disagree with me, they will be ignored. So in some sense, this suggests that humans actually exhibit a degree of confirmation bias even towards AI. And you can imagine this kind of potential confirmation bias will bring up some risks. For example, if we look into humans' reliance behavior to the AI model separately for those cases when AI model's prediction is correct and those cases where AI model's prediction is wrong, what you can see here is that the pattern is exactly the same, suggesting that, humans may over-trust or over-rely on AI model simply because it agree with themselves more, and they may also under-rely or under-trust the AI model simply because it doesn't really agree with them. Okay, so that's the first thing that we find in the first project. Now, moving on to a second project, we want to sort of quantitatively categorize how exactly, what's the cognitive mechanism behind people's decision to trust or rely on AI model. So before we do that, let's actually specifically define a particular decision-making settings that we're interested in modeling now. So let's again say, we have a decision-making task. For a second, let's assume it's going to be a loan application task that people need to decide whether this loan applicant will default or not. And we say that given this decision-making task, the AI model is going to provide two pieces of information, both in terms of their binary prediction with respect to whether the applicant will default or not, and also the CM term, which is their confidence in the prediction. Okay, so now this binary prediction as well as the confidence will be moving on to passed on to the human decision maker, and human decision maker essentially need to make a decision of whether they want to adopt AI's decision or not. And we are interested in modeling how people actually make this decision of adopting AI's suggestion or not. So how can we model this problem? So let's start by assuming for a second, our decision makers are aware of the fact that their decision bring up consequences, which means that, our decision maker have some sort of a vague idea in their mind saying that, if their final decision is going to be correct, they will have a reward of 1. If their final decision is going to be wrong, they'll have a penalty of beta. Okay. Now, if we accept this assumption, then you see that the decision our human subjects is making now, our human decision maker is making now, you'll probably agree with me that they're essentially facing two gambles. The first gamble is called accepting AI, right? So accepting AI will lead, well, if we assume that the AI model's confidence is calibrated, then accepting AI will lead to a reward of 1 with probability CN, and it will lead to a penalty of beta with probability 1 minus CN. And the other gamble is called rejecting the AI, and you can also calculate the different probability for different outcome. So if we are facing this kind of gamble, you can realize that this is actually a classical risky choice problem that economists and psychologists have started for years, and they have actually developed a lot of different models to quantify, people's behavior behind this kind of risky choice problem. So then we can make use of those models in modeling our problem, right? So one possible way to adapt those models into our context is this kind of 2-component model where we decompose people's decision-making process into 2 components. The first component is that given the AI model's confidence and binary decision recommendation, we're going to estimate the utility of each gamble, utility of accepting the AI or rejecting the AI. And so this kind of model, you can go with expected utility model, or you can assume that, people have distorted the perception of the probabilities, and you apply this prospect theory in the estimation of utility. Now, after we assume this decision maker have transformed the AI model's confidence and binary prediction into the utility of these 2 gambles, we can go on for the second component, which is action selection, right? So the utility of each gamble is going to be transformed into a probability of selecting that gamble. And again, we have a lot of potential models to make use of. For example, we can assume that people with a high chance will go with the gamble gives you the highest utility, but there is a small chance that they will make mistake. Or we can go with this more discrete choice model type of logic model here. Okay, so now if we look at our 2-component model space so far, we'll realize that so far we have assumed people's final decision of accepting or rejecting AI model's suggestion is solely dependent on the AI's input, AI's information, right? Whether AI think it's going to default or not, and AI's confidence. But isn't that in the first project, we just talked about that people's own independent judgment potentially can influence the decision of accepting or relying on AI indirectly, right? So how can we incorporate this human's own independent judgment into this modeling approach? So if we assume that human, they will also form an independent judgment in their mind, and they also have a confidence in their own independent judgment, how would they be playing a role in the process of determining whether to accept AI or not? So that's the next part that we try to address in this project. So we try to adjust both the utility estimation and action selection model to reflect the fact that a human may actually utilize their independent judgment in their decision of whether to rely on AI or not. So again, starting from the utility estimation part, now what we are saying is that the utility that people came up with for each of the gamble is no longer determined just by AI's decision as well as AI's confidence. It's also going to be affected by humans' decision, independent decision, and humans' confidence in their independent decision. So, for example, we can imagine a possible way for people to have this process is they will combine the confidence in their own independent judgment and AI's confidence in AI's judgment together to form a new confidence. And this is their combined, updated confidence in how likely AI model's prediction is correct. And we can actually, once we have this combined confidence, we can put this combined confidence again into, the kind of utility model that we have discussed before, right? Like expect utility, prospect utility, or whatever other utility model that we have discussed before. But the key now is how people will actually combine these two sources of probabilities or two sources of confidence together. So there are a couple of possible ways that this can happen. So for example, people can just take a simple average of these two confidence, right? So in this case, for example, if both AI and humans think a particular applicant will not default on their loan, and one of them have a confidence of 0.7, another have a confidence of 0.9, combine them together would simply give you a confidence of 0.8. But another possible option is this naive Bayes rule, which, compared to this average rule, the key difference is that naive Bayes rule tend to push the combined probability into more extreme than the individual probability. So in this case, when we are looking at a combination of 0.7 confidence and 0.9 confidence, after combining them together, people think, oh, there is a 0.95 chance that the AI is making a correct prediction. Okay. Now, we have explored some other combination rule as well, which is essentially an average of a trade-off or a middle point between this average rule and the naive Bayes rule. Okay, so that's for how we take humans' independent judgment into consideration in the utility estimation part. But moving on, we have the action selection part as well. So how can we take humans' independent judgment into consideration in the action selection part? Again, what we assume is that the probability for people to take a particular action or take a particular gamble is not only decided by the estimated utility anymore. It's going to be directly influenced by the human's judgment as well as AI's judgment. So for example, we can assume that after people have used the sound action selection model to decide the probability for selecting each gamble, they may actually further update this probability based on whether the AI's prediction is aligning with their own independent judgment and how confident they are about their own judgment. So, for example, one of the updating rule could be something like what I'm showing to you here on the screen. Essentially, what this updating rule says is that if human and AI are agreeing with each other, they will increase the chance that they are going to follow AI's or accepting AI's decision recommendation. And this increase will be larger if humans are more confident about their own independent judgment. Okay, so now I have laid out, a space of possible models for us. And let's then just look into which of this combination of model actually fit the real world data the best. So that's what we did. So we actually collected some human subjects' decision in predicting loan default, and we fitted our different combination of model with this data that we collect. So what I'm going to show you is the comparison of these different models' performance in terms of a negative log likelihood. And for negative log likelihood, the lower the value, the better. Okay, so here is essentially what we get. So this is a very crowded plot, but let me just go through each one of them together with you. So if you look at the gray bars represent the different combination of actions, utility estimation and action selection model when we don't take human adjustment or humans independent judgment into consideration in neither component. Okay, so we don't consider human adjustment in neither the utility estimation nor the action selection part. Now, the colorful bars that are transparent on the background are indicating the case where we actually incorporate the adjustment in the utility estimation part, owning the utility estimation part. Okay, so and different color or different bars essentially representing different rules for people to combine their confidence together with AI's confidence. So essentially we see that, when we incorporating the human's independent judgment into this model, owning the utility estimation part, it makes some improvement, especially in the case when we consider the human's action selection model is going to be taking a logit model. Now, the colorful bars in the front ground are those cases that we take humans' independent judgment into consideration in both the utility estimation part and action selection part. So what we see here is that those are particularly performing well in fitting the data that we have in hand. And in particular, they are performing really well when we are thinking of in the utility estimation part, people are aggregating their own confidence and AI models' confidence using this adjusted naive Bayes rule. Okay, so this gives us some idea of how to model the human's decision of whether to rely on AI or not. But this model can actually give us more information. It can sort of help us to explain why people behave this way or that way in different decision-making contexts. For example, what we did is, we repeat this experiment, but this time we vary the decision-making stake, essentially that beta, right? The beta representing whenever you make mistakes, how much penalty you receive. So we created two sets of data with, a high decision stake or high penalty versus low penalty. And we try to learn the model for each set of data and see what's the difference. So in this case, we focus on this particular combination of model, which is in the utility estimation part, we took this prospect theory-based utility, and we use adjusted naive Bayes rule to combine human confidence and AI confidence. In the action selection part, we use the logit selection model, and we also take humans independent judgment into consideration. So if you look at this particular model combination, you see that in this prospect theory or the utility estimation part, essentially what it did is that it starts with machine AI's confidence and their own confidence, combine them together to form a combined confidence, and then they will map this combined confidence into distorted probability, right? Remember, we have this prospect theory, which says that people have a distorted view of probability. So this B as an outcome is actually people's final belief in how likely AI is going to be correct. And what we did is that we keep the combination of AI confidence, the original AI confidence and original human confidence to be exactly the same. And we estimate what this B value will be when decision stake is high versus decision stake is low. And what we find is that in most of the cases, when you have a higher decision, people are more likely to believe the AI is less likely to be correct. This is under the condition that you have exactly the same combination of AI's original confidence and humans' own confidence in their independent judgment. Now, moving on, once you get this confidence, what you will get later in the action selection part is that you are going to map this belief in AI confidence, belief in AI correctness into a utility of the accepting AI gamble. And with this utility, you're going to decide what's the probability for you to accept AI's decision recommendation. But because of this adjustment, before we actually take the action, what we're going to do is we are going to compare AI's decision or AI's recommendation with our own independent judgment, and combined with our own confidence in our judgment, we're going to eventually adjust the probability a little bit and make a final decision in determining whether to accept AI's decision or not. So now in the second component, what we're going to do is that if we fix the B value, which here it represents our belief, our combined belief of AI decision recommendation being correct, we'll look at how likely this final probability of accepting AI's decision recommendation is going to change when you have high stake decision, when you are dealing with a high stake decision versus when you are dealing with a low stake decision. And what we find here is that if your own independent judgment is agreeing with AI's decision making, basically, the higher the decision stake, the more likely it will make you to adjust in accepting the AI recommendation. But if your own decision is in disagreement with AI's decision, the higher the decision stake, the more likely this disagreement will lead to a decrease in the probability of accepting AI's decision recommendation. Okay, so this is some additional insights that we have learned from this modeling process. Finally, let me very quickly give you introduction for a third project in which, once we have this empirical and computational understanding, we try to see whether designs on intervention is possible. So in this case, do I see? Okay, so I thought there are some questions, but let me just continue first. In this case, our goal, our intervention design goal is, of course, to try to promote human AI complementarity. We want to have the human AI team to have the best possible decision-making performance. And in order to achieve that goal, ideally, we want human to be able to combine their own wisdom intelligently with the AI's recommendation or AI's intelligence. Right? But up until now, what we see is that in the first project and the second project, a common thing that we see is that humans are indeed making use of their own wisdom. They're utilizing the information that is embedded in their own independent judgment and decision confidence. But they're using it in a not ideal way. They're using it to gauge whether they should trust the AI model or not. And they're using it in a way that's not really differentiating when AI is right and when AI is wrong. So really, our goal here is how can we help humans to better combine their own intelligence with AI's intelligence? Or in other words, how can we help humans to utilize their strengths and avoid their weakness? And this is something that we explored recently. And our idea is actually quite simple. So we think that in order to help humans utilize their strengths and avoid their weakness, we first need to figure out where is humans' strength and where is humans' weakness in comparison to AI. So this is essentially saying that if it is possible for us to estimate on a particular decision-making task, what is the likelihood for human to be correct on it, and what is the likelihood for AI to be correct on it? If we have this information, then it seems to be an easy problem because we can guide human to rely on AI if AI is more likely to be correct, and we can have human to guide to rely on themselves if they themselves is more likely to be correct. So this idea is very nice, but here are two key challenges, right? So the first challenge is how can we actually estimate humans and AI's correctness likelihood on the decision-making task in the real time? In most of the cases, in the real time means we don't even know what's the ground truth for that task, right? So for AI, this probably is slightly easier because we can assume or we can try to calibrate AI's confidence. And so AI's confidence could potentially serve as a correctness likelihood indicator. But this problem is particularly tricky for a human. So the first key challenge is how can we estimate humans' correctness likelihood in the real time. Now, the second question is, even if we have this information, how can we successfully nudge human to either rely on themselves or rely on the AI? Right? So these are the two things that we're after here. So let's start with the first challenge, how to estimate humans' correctness likelihood on some tasks that we probably don't even know the ground truth answer. So here we are making a key, but somewhat intuitive assumption. We say that a person's decision accuracy on a task is likely to be correlated with their decision accuracy on other tasks that are similar to this task. Right? So if you are likely to be correct on other tasks that are similar to your current task, you're also more likely to be correct on this current task. So this essentially says that in order to estimate this human decision maker's accuracy on a particular task, we probably can just look at how frequently this human decision maker makes correct decision on other tasks that are similar to this one, and we also know the ground truth for those other tasks. Okay, so with this in mind, we take a four-step procedure to actually enable this estimation of humans' correctness likelihood. So basically, for a particular human decision maker, when they come into our setup or coming to make decisions, we first give them a set of representative decision-making tasks for them to actually indicate what their decision would be. With those information, with those small set of decisions coming from this human decision maker, we learn a decision model of this decision maker. So this decision-making model is going to be a decision tree. And we then extract rules from this decision tree and present this tree rules back to the decision maker so that they can interactively modify them in case they think those rules are not correctly representing their decision rationale. Okay, and finally, utilizing the adjusted version or updated version of the decision rules after humans' interaction with it, we're going to make prediction of what decision this decision maker will make on each of the decision-making tasks in the training data set of the AI model. Because it's in the training data set, we know the ground truth, and because we know the ground truth, we will be able to know whether the decision will likely to be right or wrong. And now, whenever this decision maker is making prediction on the new tasks, we're going to search for those training task instances that are close enough, that are similar enough to the current decision-making case. And we will estimate this human decision maker's likelihood of making correct prediction on the current task as their accuracy on those similar training tasks. Okay, so this is how we try to estimate humans' correctness likelihood on decision-making tasks on the fly. Now, with this in mind, the next challenge to address is how to nudge people, right? So one of the most straightforward way for us to do it is just tell them, right? So we create this serve as one of our intervention. We just create an interface. We directly say, oh, here is the AI's confidence. We also made a little bit guess about you. We think you're likely to be this accurate on this task. And, these are just the information. Use it in whatever way that you want. Okay, so this is our first intervention direct display. Now, maybe people are worried about this, right? Why you're guessing about me behind the scenes, right? So then we try to say whether we can communicate this information a little bit indirectly, a little bit implicitly. So a key information here, or a key background here, is that in the HCI community, actually quite a bit of work have already done that find particular design of decision workflow and the decision interface that will lead humans to decrease their reliance on AI. So with this in mind, we thought maybe we can design some adaptive interface, meaning that whenever we find or we predict humans' correctness likelihood is going to be higher than AI, so we don't want them to rely on AI, we'll use those interface or workflows that researchers have found in the past. So with this in mind, we created two additional interventions. The first one is adaptive workflow. So in this case, if humans' correctness likelihood is predicted to be higher than AI's correctness likelihood on a particular task, we're going to first ask them to make their own independent decision on the task before we show them the AI's decision recommendation and confidence. Otherwise, we're going to directly show them the AI's decision and AI's decision recommendation and confidence. Because in this way, once we ask them to first commit or register their own independent judgment, they actually have been shown to less likely to rely on AI's confidence, rely on AI's recommendation later on. So this is our first intervention. Now, the second intervention is, again, if we predict humans' correctness likelihood to be higher than AI's correctness likelihood, we're going to only show them the AI's explanation without showing AI's decision recommendation. If the other way around, we're going to show them both the decision recommendation and the explanation. Because again, previous research have found that when people just see the AI's explanation without seeing its decision recommendation, they are less likely to rely on AI's suggestion. So we carried out an experiment to see whether these interventions can help improve the joint decision-making performance. And as you can see here in this plot, compared to a baseline treatment, we always show to people the AI's decision recommendation as well as their confidence up front. The three interventions that we used here either marginally or significantly increased the final decision-making accuracy of the human AI team. And if we dive deeper into the analysis a little bit more, we find that this increase in human AI joint decision-making performance is mostly caused by the fact that our three interventions either marginally or significantly decreased people's over-reliance on AI when AI is more likely to, when AI is making wrong prediction, and it does not cause a significantly higher level of under-reliance. Okay, so that wraps up with my today's presentation. So I hope that given this approach, three projects, we have had a little bit more understanding of both the empirical understanding of how humans interact with AI, how to computationally model their interaction, and how we can potentially design intervention to influence this process. Thank you.